Okay, so most of your earthquakes are occurring at tectonic plate boundaries, and that's where the plates are slowly grinding past each other. So tectonic plates move very slowly. They go at about the speed your fingernails grow. And most of the time they're grinding past each other at that very steady rate, but there's lots of roughnesses and asperities along those boundaries. And so they will catch and stick at various points. And we don't normally think of rocks as elastic, but they can build up stress. They do bend back like a bow, if you will, and they build up that stress along these points where the plate boundaries are sticking. But the actual movement of the plates is inevitable. They're going to keep creeping and keep creeping. But these places where they've stuck, they're bending back and they're bending back. And eventually they're going to snap. And that snap, that sudden surge along the plate boundaries is the earthquake. That's the most common form. We can have earthquakes caused by volcanoes and undersea explosions, other things too, but the most common earthquakes are caused by movements along plate boundaries, these stresses that build up and build up and build up, and eventually are released when the plate surges forward at some particular location. Magnitude measures a combination of how far the plates move, how big a section of the plate is moving, and how much energy is liberated during that release. And it's earthquake magnitudes are not on an ordinary linear scale, they're on a logarithmic scale. So every step on the earthquake magnitude scale is roughly a factor of 30 in energy released. So a magnitude 6 is 30 times bigger than a magnitude 5. A magnitude 7 is 30 times 30 or 900 times bigger than a magnitude 5. So because there's such a huge variety in the size of earthquakes, we have a logarithmic scale to explain it. So little earthquakes, magnitudes 2 or 3 or so, are so much smaller than magnitude 9 or 10. Tend to think of these scales, human mind always tends to think linearly. So it's a 6.2, it's a 6.5, it's a 7, just a little bit bigger. But no, they're not just a little bit bigger, they're a lot bigger. It doesn't technically have an upper limit, but there's a limit in how big. I mean, at some point, if we had never had an earthquake magnitude 10, it would require a fault that went almost halfway around the planet to do that. At some point, you're limited by the size of the Earth, right? There's only so much you can move. But yeah, I mean, because remember that scale is increasing so rapidly each time. Yeah, we've had some very big ones, but it's, you know, these are the once in a century type quakes. So I mean, there's a background of earthquakes all the time. If you look at the U.S. Geological Seismic Map, you'll see the plate boundaries are basically delineated by all these little earthquakes that are occurring all the time. And then every now and then you get the really big one. You know, that's the thing about earthquakes. That's what makes earthquake prediction so difficult. When you think about earthquake prediction, there's basically what's called long-term forecasting and then there's short-term prediction. So long-term forecasting looks at plate boundaries that are active and says, well, on average, every 50 years or 100 years, you're going to get a magnitude such quake here, right? That's kind of like long-term climate prediction or long-term weather forecasting. You know, we get thunderstorms in the summer. Yeah, we know that, right? It says nothing about when a particular earthquake is going to occur. We know the San Andreas, for example, is an active fault. We know that it had the big earthquake in the late 1800s. We know that at some point it's going to have another really big earthquake. That's the long-term forecasting. The short-term forecasting, earthquake prediction, which everyone would like to have, would tell you that you're about to have one, right? Well, we don't have anything that does that, and that's because the stresses are building and building and building, but it's so hard to know exactly when it's going to snap. You know, you can watch the straws being piled on the camel's back, but you don't know which one is going to be the one that finally does it, right? So right. All year long, the plates are moving, they're moving, they're moving. For hundreds of years, they're moving. We don't know when they're finally going to go. And that's been a real bugaboo for earthquake seismologists for a long time, because everyone wants an earthquake prediction system. And all we can give you is a percent probability in the next 5 years or 10 years that it's going to happen. We can't say when and where it's going to happen. Interestingly enough, in recent years, we have developed earthquake warning systems. Now, a warning system is something that's like when you have a tornado warning, it means the tornado's been seen. It's on the ground, right? You need to go hide somewhere. So we actually have a way when an earthquake has taken place to provide some warning that the earthquake waves are on its way. The problem is the warning isn't very long. It's on the order of 10, 15 seconds. And actually, I have an activity I do in my earthquake class, my general education class, Disasters, Geology versus Hollywood, where I tell the students to exchange phone numbers and then text the other student at a random time that there's an earthquake in 15 seconds. And then they're supposed to keep a log of what they do for those 15 seconds. You know? And of course, you get under a table, or stop the car and get off the bridge or something you can do it. But what's interesting, and the reason why this is valuable, and actually it's coming to California, they're developing the same system right now. The reason why it's valuable is that although 10 or 15 seconds doesn't sound like very much to you or I, to a computer, it's a lot of time. And so for things that are under automated control, there's a lot you can do in that time. You can bring the bullet train to a stop. You can shut down the power grid so we don't have electric fires started off, right? You can stop elevators at the nearest floor and get everybody off. You can tell the surgeon to get his hand out of the patient's chest. There's actually a lot you can do in 15 seconds if you're a computer. Well, I guess the thing to know about earthquakes for people in general is that it's not earthquakes that kill people, it's buildings that kill people, right? So if you were in the middle of an open grassy field and a magnitude 9 earthquake occurred, you'd probably be knocked in your butt, but that's probably the most it would do to you. They break gas lines and power lines and start fires. They create avalanches and cause roads to fall down. They create tsunamis if you're near the coast. But it's not the earthquakes, it's not the vibrations that do the harm. And so the biggest risk for us on the East Coast is our building structures. Another interesting thing for telling students about is if you wanted to understand earthquakes, you also have to go back into the past because they occur so rarely on the East Coast, right? We only had seismometers around for about 100 years. And earthquakes, we're talking about the definition of an active fault is one that has moved in the last 10,000 years. So how do we get information on earthquakes going further back into the past? Well, one of the things we do is we look at people's written records and they write down experiences that they had. And so there's actually a second earthquake scale called the Mercalli scale that is not based on seismometers. It's based on written descriptions of what people have seen, right? So for example, one real common thing for people to write down is that their chimney fell off. Because when a building shakes, it's not enough to collapse the building. The one thing that tends to vibrate loose is the chimney. So that's actually on the Mercalli scale. Another real common phenomenon is whether or not the chandeliers shake. For a minor earthquake, they'll vibrate, right? And people will say, oh, the chandelier shook and the glasses in the cabinet rattled. Well, that's a lesser earthquake than one that toppled the chimney. And often another real common one is the grandfather clock stopped. Everyone used to have a grandfather clock. And if the grandfather clock stopped, it took a certain amount of vibration to cause that. And they have taken these Mercalli scale and they've calibrated against modern earthquake magnitudes. And they can make rough translations between how big the earthquake was and where it was occurred. And of course, if people are living in different places and the people in this city, their chimneys fell, but the people in this city just had the glasses rattling, you can triangulate back on where the earthquake occurred from the description of what people experienced. The USGS is still taking advantage of that now. They have a site called Did You Feel It? Where people can tweet when they felt an earthquake. And interestingly enough, some of the really small earthquakes that are not always picked up in our networks are tweeted about by the people that live right there. And you also can see people all Googling the earthquake website. So wherever there's been an earthquake, lots of the IP numbers from that place will Google the earthquake website at the same time. And we'll go, oh, they must have felt something.
Discover more at ambler.temple.edu/science of scary.